So let's go ahead and do a few more problems together from 4.5. Hopefully you had a chance to redo those ones that we did together and that you feel pretty comfortable with those types of problems. But let's go ahead and do number 28. The half-life of thorium-229 is 7,340 years. Again, what does it actually mean? That means it takes 7,340 years for half of whatever the amount started with to decay or to go away. So again, that's a pretty long half-life. And it says, how long will it take for the sample of this substance to decay to 20% of its original amount? So we're going to start off with that A equaling A naught E to the KT. Again, you do need to have these formulas memorized. Now, what information have they given us? Well, not a whole lot. They've only told us that the half-life is 7,340 years, and we want to know how long will it take to decay to 20%. So we need to definitely find the rate. And the rate for half-life was the natural log of a half divided by the half-life. So let's go ahead and put this into our calculator, and we have the natural log of a half divided by the half-life for this is 7,340 years. So typing that in, we have natural log of 0.5 divided by 7,340, and we get that. So if you've never seen this in your calculator, the e to the -5 actually represents scientific notation. So it'd be like 10 times 10 to the -5th. So that means we need to move the decimal 5 places to the left. And again, when we do that, the first one will be in front of the 9, and then we'll have 4 more zeros. So k is going to be approximately -0.4, and then 4 say -0.00009. So on the test, I'd probably want you to go to the 4, but with their directions, they just said round to the first decimal place. So -0.00009. All right, so now we have A equaling A naught E to the -4 zeros, and then 9t. And the question wants us to know how long will it take for a substance to decay to 20% of the original amount. So we don't know the original amount, so we need to take 20% of the original amount would be my final amount A. So 0.20 times A naught equals A naught E to the -0.00009t. I want to challenge you not to memorize these things, but to understand why we're doing what we're doing, because things do change. So just make sure you're understanding the process and the concept, not just how to set up the original problem. So the A naughts will cancel, and I have 0.20 equaling E to the -0.00009t. Then we're going to need to change exponential into log. So log base E of 0.20 equals the exponent. So log base E we call ln of 0.20 equals -0.00009t. And all we need to do is divide by that decimal to get t by itself, and that will tell us how long it would take to decay to 20% of the original amount. So natural log of 0.2 divided by -0.00009. So we end up with that. So it'd take about 17,882 years. Again, it all depends on how far you go out on your decimal. Sometimes it'll be a little bit different in the answer. So just know that on the test, I want you to go out to, say, 3 decimal places past all the zeros. So that would point 409 and then your 44. So again, this is going to look different than the answer because of the fact of where we go on our K. So T would be approximately 17,883 years. All right, so now let's try one more of these. We'll talk about aspirin in the bloodstream. So let's go ahead and look at number 30. Again, I hope you have these in front of you because I might not get to show everything the whole time. So, number 30. The half-life of aspirin in your bloodstream is 12 hours. How long would it take for the aspirin to decay to 70% of the original dosage? So we're going to look at number 30. Again, we're using the formula A equaling A naught E to the KT. This is the same type of problem that we just did. They did tell us that the half-life is 12 hours. So K would be the natural log of a half divided by the half-life. And in this example, the natural log of a half divided by the half-life of 12 hours. So K would be approximately natural log of 0.5 divided by 12, which would be approximately negative 0.0578. So on the test, I'd like you to go 3 decimal places past all the zeros. So we'll go ahead and start it that way. So A equaling A naught e to the negative 0.0578 t. Now this example says they want 70% of the original dosage. So 70% of A naught would equal A naught e to the negative 0.0578 t. So we'll continue like we've done every other problem, divide by the A naught, so the A naughts cancel. We get 0.70 equals e to the negative 0.0578 t. Then we'll go ahead and do the circle, changing an exponential into a logarithmic. So when we do that, we get the natural log of 0.70 equals negative 0.0578 t. And then all we got to do is divide by that decimal to get t by itself. So we're going to have natural log of 0.7 divided by negative 0.0578. So how long will it take? And we'll just round to the nearest second decimal place, so 6.2. So we'll say t is approximately 6.2, and this one was for hours, so 6.2 hours. It would take that long for it to go to decay to 70% of the original dosage. So I hope you feel fairly comfortable with the percent problems. Again, there's all kinds of different ones you could get. Let's go ahead and try one more together, and maybe a couple more. Let's look at 36. So 36, we have used, they give you a little bit of information, make sure that we just know these formulas by memory, and all I'll give you is what 35 says. So the growth model A equaling 4.3 e to that decimal describes New Zealand's population in millions T years after 2010. So we're going to look at 35. Let's do 36 because 35 will have the answers in the back. So let's go ahead and do 35. So growth model A equaling 112.5 e to the 0.012 t describes Mexico's population, A, in millions T years after 2010. So what is Mexico's growth rate? Well, again, this is the rate up here, and when asked for the growth rate, make sure you put it as a percentage. So we're going to take the 0.012, we're going to move it twice to the right, so the growth rate will be 1.2%. So make sure you understand the K it into a percent. All right, and then part B says how long will it take for Mexico to double its population? Well, how do we know what the population is? Well, first of all, this model starts in 2010, so 112.5 is the initial amount. So if we want it to double, we need 112.5 to be multiplied by 2, and that would give me A. So 112.5 times 2 would give me 225, and that would be A. Since we wanted it to double, this is the initial amount, so we're going to multiply by 2, we get 225 equals 112.5 e to the 0.012 t. So if we want it to double, we're just going to multiply that initial amount by 2 to get what A is. Well, just like every other problem, how do we start it off now? We go ahead and divide by 112.2, 112.5, divide by 112.5, and guess what you're going to get? 225 divided by 112.5, you're going to get back to 2. So we have 2 equals e to the 0.012 t. Then what do? The circle to change exponentials into logs. So log base e is ln. So ln of 2 equals 0.012 t. Divide by 0.012, and that's going to give us the time it takes to double. So natural log of 2 divided by 0.012, and there's whole year, so 58 years. It'll take 58 years for the population to double. All right, so one last problem we're going to do. It's called a logistic growth function Don't worry, I would never ask any of you to come up with it on your own, but I do want you to be able to use a logistic growth function, which is kind of like what would be happening right now if we looked at a function for COVID-19. So looking at, let's say 37. So last one. 37 says the logistic growth function f of t equaling 100,000 divided by 1 plus 5,000 e to the negative t describes the number of people, f of t, who have become ill with the influenza t weeks after its initial outbreak in a particular community. So we could definitely be doing this with COVID-19. So the first thing says how many people became ill with the flu when the epidemic began. Well, when the epidemic began, that means t would have to be 0. So we're going to put a 0 here. So we're going to have 100,000, be careful how you type this in, 100,000 divided by parentheses, 1 plus 5,000. And then I'm not going to raise e to the negative 0 because I know anything to the 0 power is 1. So it's just going to be 1 plus 5,000. So how many people were sick when the epidemic began? About 20 people. So approximately, f of 0 is approximately 20 people. So about 20 people were sick when the epidemic began. Part B says how many people were ill by the end of the 4th week. So the 4th week just says that t be 4. So f of 4 would equal 100,000 divided by 1 plus 5,000 e to the negative 4. Again, be very careful how you type this into your calculator. So 100,000 divided by parentheses, 1 plus 5,000, bring up your e, raise to the negative 4, and then close your parentheses so you keep your whole denominator together. So after 4 weeks, how many people are sick? When at first there were only 20, now there are 1,080. So you can see how it definitely grew. This is the same thing that's happening right now. Hopefully it'll be going down with COVID-19. So after 4 weeks, there were 1,080 people who were sick with the flu. And then lastly, it does ask one more question I probably would not ask, but what is a limiting population? Well, that's your 100,000. That's as many people that are in your population at the time. So, all right, so that's it for the word problems. I would try each one of these again and make sure you can do them before you try your homework.